The surprising truth about AI design is that generating wild shapes is the easy part. The hard part is proving those shapes are safe, buildable, inspectable, and certifiable. Under real uncertainty, that proof is the bottleneck, not creativity. In practice today, the winning approach is hybrid. Classical engineering optimization still carries the load. Literally and legally, AI helps propose candidates, learn fast surrogate models, interpret messy constraints, automate the workflow, and support human review. But it rarely holds full design authority by itself. That is not just a temporary compromise. It reflects where the real friction sits, which is qualification. One major value zone is topology-optimized lattice structures. These are lightweight internal geometries that can be extraordinarily strong for their mass. Additive manufacturing makes them practical because printers can build complex internal channels that tooling can't reach. So the combination matters. Optimization finds unusual load paths, and additive manufacturing can actually produce them. A documented 2025 workflow in China's precision equipment industry linked AI-driven design, topology optimization, lattice structures, and additive manufacturing. The point is simple. The loop can work outside the lab, but once you can generate and print lattices, you immediately collide with real-world variability. Process drift happens. Defects are not evenly distributed. Load cases are incomplete. And that leads to the central constraint for leaders. Qualification-grade robustness is the gate. A generated geometry is not a product until you can defend it under uncertainty. Loads are never perfectly known. Materials vary. Additive processes introduce anisotropy and residual stress, and sometimes hidden internal flaws. Inspection has blind spots. And life cycle degradation adds more uncertainty, like fatigue and corrosion. The strategic question becomes, how do you qualify designs when the model, the process, and the environment all move? Surrogate models add another pressure point. AI can approximate expensive solvers, which speeds early exploration. But the trust boundary is delicate. A surrogate can be a fast filter, and it can also sound confident outside its training envelope. In safety-critical work, treat the surrogate as a screen, unless it is continuously checked against high-fidelity simulation and physical tests. Knowing when to switch from cheap and broad to slow and defensible becomes a core operational skill. Manufacturability also has to move upstream into generation itself. If AI proposes shapes that are elegant in math but unreliable to print, you waste time and add risk. Additive manufacturing brings constraints that need to be encoded early, like minimum feature sizes, thermal distortion, residual stress, and surface finish. Then add inspection access, repairability, and scrap probability. A design you cannot inspect is a design you cannot certify, even if the simulations look perfect. There is a quieter failure mode too. Objective function drift. Generative systems optimize what you measure. If you reward mass and stiffness, you can accidentally harm maintainability or field repair. If you reward cost, you might increase carbon intensity or supply risk. We see this pattern across domains, from packaging to cloud optimization. The scoring function becomes the hidden constitution of the system, so the human role does not disappear. It changes shape. Human-AI collaboration needs to be treated like a control system, not a vibe. Prompts, constraint files, model versions, solver settings, and approvals need to be logged. If you want repeatable outcomes, you define roles, review steps, and escalation paths. You do not rely on informal judgment and memory. Governance questions arrive fast, especially around intellectual property and accountability. If a geometry reflects human prompts, vendor model behavior, training priors, solver outputs, automated ranking, and manual edits, who owns it, who signs it, and who carries liability after a failure? Without clear provenance and responsibility, scaling becomes a legal and operational hazard. Security is part of governance now too. Treat the design pipeline as a cyber-physical system. The threat model includes malicious prompts, poisoned design libraries, hidden stress risers embedded in geometry, tampered solver outputs, and exfiltration of proprietary parts. Red team the workflow before you trust it with high-value components. Across time, a realistic trajectory emerges. Near term, hybrid pipelines become normal in high-value teams, especially where simulation, additive manufacturing, and digital thread infrastructure already exist. Mid-century, certified design envelopes may allow machine-generated components in bounded categories, with automation handling routine verification and humans governing exceptions and liability. Longer term, optimization expands from single parts to assemblies with graded materials, embedded sensing, and lifecycle constraints, often tied to digital twins. Fully autonomous design to certification for safety-critical parts, without human authority, remains speculative because standards measurement and liability are unresolved. For capital allocation, the punchline is blunt. Build the verification stack before you scale the generation stack.